In this video, I'm going to go through the Edexcel A-level chemistry paper from 2018. This is paper 2, so that's organic and physical chemistry. Paper 2, Edexcel 2018. Okay. Right, the first question about alkanes. The reaction of ethane and chlorine in UV radiation produces chloroethane. Okay, so this, of course, is a free radical substitution reaction. So that is the answer there. You're swapping chlorines for hydrogens on the alkane. Right, the black smoke produced from the incomplete combustion of alkanes is due to bits of carbon, not enough oxygen to turn all the carbon into CO2 or even to carbon monoxide, so you get some solid carbon produced, which little black sooty particles. Okay, the reaction of hexane shown below. Well, it's not elimination because there's no HBr being removed. It's not hydrogenation. You're not adding hydrogen. You're losing hydrogen actually. It's not isomerization because they have actually different formulas. It's got to be reforming. Yeah, that one is C6H12 and this one is C6H14. So it's not isomerization. Reforming is the best one to put. Okay, so decalin, the number of so you've got 10. You've got to give the molecular formula. Right, without counting it up, you can say, right, so it's got 10 carbons. CH2N plus 2. That is for an alkane. Now, every time you have a double bond, you lose 2 H's. So the corresponding alkene would be CnH2n, or every time you have a cyclic structure, you lose 2 hydrogens. You've actually got 2 cyclic structures there, so you'd lose 2 lots of hydrogen, you'd lose 4, so it would be C10H, not 22, but 18, this one here. And if you want to check that, well, you've got 2 there, 2 hydrogens there, 2 there, 2, 4, 6, 8, 10, 12, 14, 16, and then on this one you've only got 1 hydrogen and that one left. Yeah, so that's 18. The question is about how catalysts work. Gaseous reactants attach to the catalytic surface by the process of, it's not absorption, it's adsorption, this one here. You'll be careful. Okay, and then desorption, of course, is when they detach from the catalytic surface. So there's a picture of a catalytic converter. Explain why the honeycomb structure is used in a car exhaust system. It's to provide a maximum surface area. There's 1 mark for that probably, for reactants to adsorb to. The 2nd mark. Okay, question about chromatography Tlc. Okay, a sample of a tripeptide was hydrolyzed, so that means tripeptide is made up of amino acids, 3 amino acids joined together by peptide bonds. Hydrolyzed means they're split with water into the separate amino acids, placed on a TLC plate. Samples of possible amino acids were also present. Okay, so they are these ones, A to G, they're known amino acids, and H is the hydrolyzed tripeptide. Okay, and they've shown the TLC plate there. So the solvent is going to move up there and the spots are carried with it. This will be the start line here. Okay, so calculate the RF value for the amino acid lysine. Okay, so lysine is, which one is it? Is A. Right, so RF value is equal to the distance moved by the spot divided by the distance moved by the solvent. The solvent front. Okay, so the distance moved by the spot is, let's see, if we say that One of those is 1 unit, is about 1.5 units. And the solvent has moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. So 1.5 divided by 10, the RF value is equal to 0.15. Two significant figures, I think, is all you can justify there, definitely. Okay, identify by name the 2 amino acids present in the tripeptide and give a reason for the lack of a third spot. Well, if you look, this spot here obviously corresponds to that one, B, so that's serine. And this one here obviously corresponds to that one, F, which is methionine. Right, why are you only going to get 2 spots instead of 3 spots as a tripeptide? Well, one of these amino acids must be used more than once. So it could be the tripeptide could be serine, serine, methionine. Or it could be, serine, methionine, methionine, or any combination of that. But you can reuse the same amino acid and the tripeptide. They don't all have to be unique individual amino acids. Okay, 2 reasons why different amino acids have different RF values for 2 marks. Well, things move in the chromatography by different amounts because they've got different affinities or liking for the solvent and for the stationary phase, which is this TLC plate. So I'll just put different affinities for 1 mark, the solvent, and 2, the stationary phase. So if one amino acid is very soluble in that solvent, it will move a long way. It will move close to the solvent front. If it's not, then it's hardly going to move at all. So vice versa. Right. In chromatography, a locating reagent is often used when the components are colorless, as is the case with amino acids. Which reagent is used for amino acids? Straightforward recall, and you either know it or you don't, and it's ninhydrin. Okay. Different kind of chromatography. Now, gas chromatography can be used to separate the components in a mixture and to determine the amount of each product present. Why are argon and nitrogen suitable carrier gases? Because they are unreactive. Okay, so you can't. Gas liquid chromatography is quite often carried at high temperatures, so you can't really do it in air because the oxygen can react with. Oxygen is pretty reactive and can react with some of the compounds in the mixture. Okay, so they've shown a chromatogram, a GLC readout. Okay, now you've got a mixture of X, Y, and Z in there. And X has got a retention time of 10 seconds. So this is the peak for X. Now it says Y has got a retention time of 15 seconds. So you're going to get another peak about here for Y. Just like write that down there. And then Z, you're going to get a peak at 40 seconds. Write that one there. Right, it says that it is 1 part X, 2 parts Y, and 1 part Z. Now the area under the peak is proportional to the amount of the stuff in there, okay? So Y, there's twice as much of it, so you're going to have Y is going to be a peak about twice as tall. It's the area under the peak really that matters rather than the height, strictly speaking though. And then Z, well, it's the same amount of Z, so you can have the same height as the X. Okay, so it would look like that. Okay, many vehicles are fitted with airbags, which provide a gas-filled safety cushion. Okay, the blah blah blah. The first reaction in airbags is the thermal decomposition of sodium azide to form sodium and nitrogen gas. Write an equation, and you don't need state symbols. Okay, so NaN3 is going to give us sodium, and nitrogen, of course, is diatomic, so it's going to be N2. So to balance that, we'd need to put a 2 there, 3 molecules of nitrogen, and 2 sodiums. Okay. Now here's the ideal gas calculation, I think. Right, in the reaction, a typical airbag is inflated by 67 dm cubed of a gas. Calculate the minimum mass of sodium azide, okay, in grams needed to produce this volume. Okay, so what we're going to have to say is we are going to have to find out find the moles of N2 we needed to inflate the bag. Okay, and from that we can then say you're going to need, so that we're going to need 2/3 that number of moles of sodium azide. First of all, let's find the moles of N2. So we use the ideal gas equation. PV is equal to nRT. Rearrange to find the number of moles of gas. So N is equal to PV over RT. Now, I've got to be very careful with the units in the ideal gas equation, particularly with volume. That has got to be measured in meters cubed. Now, the volume is 67 decimeters cubed. There are 1,000 decimeters cubed in a meter cubed, so that is equal to, divided by 1,000.067 meters cubed. Okay, so then we've got that, and what else? 300 degrees C, we have to be careful, that has to go to Kelvin. So that's equal to, add 273, that's 573 Kelvin. Finally, we've got the pressure, that's already in pascals, which is the right unit. Okay, so let's do that. So N is equal to 140,000 multiplied by the volume in meters cubed, 0.067, divided by the gas constant, which is 8.31 joules per mole per Kelvin, and the temperature was 573. Put those numbers into a calculator. So that is 1.97 moles of gas. Okay, which okay, that's how many moles of gas we've got of N2. Now we've got 2 moles of NaN3 of sodium azide give 3 moles of N2. So that means to make 1.97 moles of nitrogen, we need 2/3 times 1.97 moles of azide, sodium azide. Okay, that's equal to 1.313 moles of sodium azide. Right, and but it asks us to find out the mass of sodium azide in grams, so we have to do mass is equal to moles multiplied by the MR. The moles is 3.13. Sodium azide, MR sodium azide, is going to be 23 plus 3 times 14 for nitrogen, which is 65. So that mass is equal to 85.36 grams. Just think about, I think we should give this to 2 sig figs because that's the least accurate bit of data there. So we should give that to 85 grams. Okay. In the second reaction, the airbag is between the sodium produced in the reaction and potassium nitrate. Okay, to get rid of the sodium because the sodium is reactive and obviously you don't want it hanging about. So balance the above equation, justifying the answer in terms of changes in oxidation numbers. Okay, so let's have a look at that. Right, sodium has got an oxidation number of 0 there, and it's got an oxidation number of +1 there. So that means the sodium is, each sodium is losing 1 electron, but there's 2 sodiums there. So that's right, each loses 1 electron. Now potassium nitrate, nitrogen changes its oxidation number there. Potassium doesn't, that stays as +1 throughout, ignore that. Oxygen is always -2, so ignore that. But nitrogen will change its oxidation number there. Now the nitrogen potassium nitrate has got an oxidation number of +5. Whereas in here it is 0. The uncombined element is 0. So let's call that half N2. So that means that is going to gain 5 electrons. So that means for every 1 nitrogen, we are going to need 5 sodiums. So let's say for 2 nitrogen, so with 2 nitrogens, you're going to need 10 sodiums. So I'm going to put 10 there. So that means we're going to have 5 Na2Os, okay? And we have got 2 nitrogens to worry about, so we need to put a 2 in front of the potassium nitrate. And then we've got 2 in there anyway for the nitrogen, so we don't need a number there. And we don't need a number in front of the potassium oxide. And if you just check your oxygens, I think they are all right. We've got 6 oxygens on the left, 6 on the right. Yeah, that's fine. Okay, so that's that. So you just do it in terms of the number of electrons lost by one atom, one element has got to be equal to the number of electrons gained by the other. Okay. Okay, the third reaction in the airbag is between the metal oxide and silicon dioxide. Okay, so we've got metal oxides, so we've got potassium oxide and sodium oxide. They are both, state the type of reaction and justify as to why it's necessary. Right, these are both basic oxides, whereas silicon dioxide is an acidic oxide. So you're going to get a neutralization reaction there. To make a silicate, silicate ions contain that ion. Okay, that's a silicate ion, which is very similar if you think to a carbonate ion. Carbon's always also in group 4, like so. Okay, so the way I always remember it, silicate ion. Okay, now why do you need to do that? Is because both of these are they dissolve in water. They produce very alkaline solutions. They are corrosive. Okay, or caustic. Whereas silicates are pretty harmless. Yeah. Okay, so I think your 3 marks is covered by all of that. Right, Maxwell-Boltzmann distribution shows the molecular energies. Okay, so this is a Boltzmann distribution. Now, when the airbag cools, well, this is kind of like, this is the, not strictly the average energy, I think it's the mode energy, you'd say it was, of the particles here. So that's got to, that peak has got to move that way when it cools down. But we've also got to ensure that the area under the curve stays the same, because that's equivalent to the total number of molecules. So that means we've got to draw this peak to the left, and it's got to be slightly higher, because that will be the distribution at lower temperature. So the area under both curves is the same. So you've got to be to the left and higher. Shift to the left and it would be higher. Left because the average energy of the molecules has gone down, or the mode energy has gone down, and higher, well, that's to ensure that the area under the curve is the same. Right. Alcohols can be oxidized by acidified dichromate. Balance the ionic half equation for the reduction of dichromate ions and give the colors if they are colored. Okay, so let's do that. Well, we've obviously got to put a 2 in front of the chromium ion there. Right, that means we have got 7 oxygens to get rid of there, so we need 7 H2O. So that means we will need 7 times 2, 14 H plus ions. Now we need to balance the charges. So we have on this side, we've got a total charge of +6 at the moment, 2 times 3, +3. On this side, we have got a total charge of 2 minus, add 14 pluses, so that's +6, +12, sorry. So to make the charge the same over the side, I need to add 6 negatives here, 6 negative electrons. That's that. You probably know that equation off by heart anyway because it's a pretty familiar one. Right, colors then. Well, potassium dichromate is orange, and the chromium ion is green. You've got to know that. Everything else is colorless there. Okay. Okay, refluxing to carry out the oxidation of alcohols. This Liebig conductor has been set up incorrectly. Okay, add shading to show the water flow in the condenser. Right, what's wrong here is the water should be coming in at the bottom there, so that the water level fills up the entire jacket. And the water should be coming out at the top. Now, if you've done it the way they've done it, the water would just sort of flow like that and out. It wouldn't necessarily fill up this entire jacket with water. So you just got to show something like that. Right. Next bit then. How do the granules prevent bumping? They allow the formation of small molecules during small bubbles during boiling, rather than allowing large bubbles. Just lots of small bubbles rather than one large bubble when it's boiling. That's what I'd say there. Okay, this carboxylic acid can be produced by the oxidation of an alcohol under reflux. Which alcohol would be oxidized to produce this carboxylic acid? Well, let's just look how many carbon atoms we've got here. We've got 1, 2, 3, and we've got a methyl group stuck to number 2. So that's 2-methyl propanoic acid. So we can say that it's not that. It's got to have prop in it. Okay. No, it's not propan-2-ol, because if it was propan-2-ol, that's a secondary alcohol. You wouldn't get a carboxylic acid. You'd get a ketone, wouldn't you? If it was propan-1-ol, there's propan-1-ol. Yeah, that would be oxidized. The primary alcohol would be oxidized to carboxylic acid. And you have got a methyl group on carbon number 2, so 2-methyl propan-1-ol is the answer there. All right, 2 marks. Using the apparatus for distillation instead of reflux is not an efficient way to produce ethanoic acid from ethanol. Right, just do a very quick sketch. You wouldn't draw this in the exam, but I'm going to draw it. Distillation is going to look something like that. And there's your condenser. You've got your ethanol and your dichromate, the acidified dichromate oxidizing agent. Okay, so what would happen is when you oxidize ethanol one step, you'd get ethanal. Ethanal has got quite a low boiling point compared to ethanol, and ethanal would then come away from the flask and go in the condenser. And really, you want that ethanal to go back into the flask to get the second step of oxidation to the carboxylic acid, but it's going to evaporate away from this mixture, which contains the oxidizing agent. Okay, the hydrolysis of halogenoalkanes now. Devise an experiment giving outline details only that would enable the relative rate of hydrolysis of the haloalkanes to be compared. Right, so what happens is we're going to rely on, if you remember this experiment, it's a required practical. If you've got, like, say, bromoethane, and you react that with water, it's hydrolysis, you're going to end up with the alcohol. You'll get an H+ ion, and you'll also get a Br- ion. Now, Br- ion, you can detect the presence of the Br- ion because Br- ions will react with silver ions to form AgBr, which is an insoluble solid, so you get a cream precipitate. The same would happen with chloroethane, and with iodoethane you get a slightly different colored precipitate each time, if you remember. So we're going to time how long it takes for a precipitate to form. Right, a couple of things that we have to say there. So you're going to get 3 tubes, one for the chloroalkane, one for the bromoalkane, and one for the iodoalkane. Now in each tube, you're going to put in there not just water and silver nitrate, because haloalkanes are not that soluble in water. So you would want like a 50-50 mixture of silver nitrate solution in aqueous solution plus ethanol. And the ethanol is to help the haloalkane dissolve. You want half water, half ethanol in there. And then to make it a fair test, you are going to add 1 drop of haloalkane from a glass pipette. And if you do that, the drop sizes are surprisingly similar. Well, they're more or less the same size. So that's probably a good enough way to control the volume. But you do need to say that you're going to add the same amount of haloalkane every time. Also, to make this experiment happen over a suitable time scale, you're going to have to warm it up a bit. So you probably want to put all the tubes in a water bath. And if you say all that, you've covered all the marks there. Right. Explain the trend in rates of hydrolysis of 1 chlorobutane, 1 bromobutane, 1 iodo. Right. The rate of hydrolysis as you go is, I'll draw 1 iodo there. Well, it increases. Okay. Gets faster. And what's the reason for that? Is because the strength of the carbon halogen bond gets weaker as you go down the group. As the halogen atom gets bigger, the bonds get longer, and so they get weaker. And so they're easier to hydrolyze. For 2 marks, that's all you need to say there, I think. Okay, the product now, got chiral molecules. The product of hydrolysis of 2-bromobutane is butanediol. Both molecules are chiral. So what is meant by the term chiral? It means it has got an asymmetric carbon atom. Okay, it's got an asymmetric carbon atom. That means with 4 different groups attached. And I think we should be on the safe side here and say, so it gives rise to the 2 enantiomers. The 2 enantiomers are I will definitely get this in non-superimposable mirror images of each other. Right, so use a 3-dimensional diagram to butanediol. So here's butanediol, not in a 3-dimensional diagram, but just to show why it is chiral. So this is a chiral carbon because you've got a methyl group, an OH group, an H group, and an ethyl group. In my diagram, I'm going to write that down as C2H5. So let's draw a 3-dimensional diagram. So we want our chiral carbon here. Let's have our hydrogen sticking up. This wedge means that's coming towards us, the OH. That straight line means that that bond is in the plane of the paper, and there's our CH3 group. And then dotted, so that means it's going back into the plane of the paper. We've got the ethyl group there. So that's 1 enantiomer. And the other one, let's draw the mirror image of it. So pretend that green line is a mirror. It's going to look like this. So we'll have the hydrogen still sticking up in the air. But the ethyl going back in there this time on that side. We've got the OH there, and we've got the CH3 in the plane of the paper. So there's the 2. That's how I draw them. You should always draw them like that. Okay. Now, a 6-mark question here. Compare and contrast the mechanism of hydrolysis using aqueous potassium hydroxide of the primary haloalkane, RCHX. So let's draw that. With the tertiary haloalkane, so it's got 3 alkyl groups. R, so it's got X there. Let's call that R1 and R. Okay, they don't have to be the same. Right, now, what is the difference in mechanism? You probably remember they're both nucleophilic substitution, but this one occurs through an SN2 reaction. And this one occurs through an SN1 reaction. Let's do the SN1 reaction first. Well, what happens is it says you don't need to draw curly arrows, right? But what's going to happen? The pair of electrons in that bond are going to go into the halogen. Okay, you don't need to draw that, but so that's going to leave behind a carbocation. That carbon has got a positive charge on it. That's very reactive, and then that is going to react with very quickly with NaOH minus ion from the potassium hydroxide that's hanging about, and it's going to form the alcohol. Okay, so we're going to get a carbocation, definitely say that word, carbocation intermediate. Now this is the rate determining step. This is slow, forming the carbocation, and this one is very, very fast. So that means the reaction is, that's why it's called SN1, is because it's dependent only on the concentration of the haloalkane. So rate is proportional just to the concentration of the haloalkane. It's independent of the concentration of the hydroxide ion. But let's contrast that with this one here. So what happens here is the OH comes along, and before the halogen has chance to leave, it forms a loose association with the OH. So, and that is so that forms the transition state. So you're going to end up there with, so we've got the halogen still kind of attached, the OH minus, not quite attached. So we'll put a negative charge on all of that there, and then you're going to have the hydrogens here. Okay, now what happens then is the X leaves and the OH stays, and you end up with, I'm missing R group off there as well, aren't I? You end up with the alcohol. The primary alcohol. Right, that occurs in one step. This is called a transition state. No carbocation involved here. There's no slow step and no fast step, okay? And that means that the rate is dependent upon the concentration of the haloalkane and the concentration of the OH minus. So it's a second order reaction, whereas this one would be a first order reaction. So that should cover all of that. Okay, I'm going to leave that there and continue with this paper in the next video.